so far we discussed the many things, right? Introduction to machine learning, then neural network, as well as SVM, the linear part, right? If we have the data which are linearly separable, we could able to find the boundary, right? And we will be discussing the nonlinear part of SVM. Another thing we are supposed to discuss today, actually, that was the main topic, the deep learning models, actually. And as I said in the beginning, the underlying mathematics is the basic stuff, the neural network or whatever, perceptron learning, as well as SVM. These things are applied into the deep neural network. So I will be discussing that, and there is not many things to discuss. I will be discussing mainly the philosophy of several models, depending on the different problems people have invented, or how the learning methods have evolved over the time. Okay, so I'll introduce a few, and I do not think that will take very long time as I shared the notes or the presentation, whatever I prepared. But there are several other lectures available in YouTube. I will, and depending on your specific need, we can discuss that later if you want, or you can refer to several notes. I will refer. If you need any specific topic to learn, please contact me in my email ID, or you can call me, send me a message in WhatsApp or wherever you want. I can convey you the required note or references. Okay. Anyway, let us complete the important part of the SVM, support vector machine. So how to model SVM for non-linearly separable data. Yesterday we have seen one model, that is a soft margin concept, though it is not that we are finding out the curve boundary, but what we are doing, that we are compromising some error with the make higher margin between two classes. But however, the boundary is obviously a linear part. Today we will be working on to develop a model that helps us to separate non-linearly separable data. Okay. Now here, the main concept in modeling SVM in non-linearly separable data is that we will be not finding the boundary. Okay. Instead, what we will do is we will take the data set from one space to another where it is linearly separable. Okay, and we will be working in that transferred space, or in the feature space, we will refer that as. So in the feature space, we will be working on. Okay, so we'll take the data from the input space to feature space, with the expectation that in the feature space, the data becomes linearly separable. I have given one example earlier. Today, I'll just repeat those examples once again, so that you will be able to appreciate. Second thing is that this particular transformation, okay, as I said number of times, that there is a very concrete theorem of covers. Okay, what it is said is that it is always possible to transfer the data from a lower dimensional space to a higher dimensional space. Okay, in the lower dimensional space, it may not be linearly separable, but in higher dimensional space, it would be always linearly separable. It is possible. So maybe you have a data in 2 dimensions. Now you can transfer the data within 2 dimensions itself, or maybe you have to take the data to 3 dimensions, 4 dimensions, 5 dimensions. If required, we can take the data to infinite dimension, where it becomes linearly separable. But there is some issues about this. The theorem does not give us that an algorithm, okay, where to take, where it becomes linearly separable. Okay, that is the issue. Anyway, that particular concept has been concept has been used here to model an SVM, so that we can take the data into the higher dimension and where it becomes linearly separable. Now, let me just repeat this example. We all know that if we have the data, XOR data, okay, which is not linearly separable. It is very clear here. XOR function we are very much familiar. Let us consider only the binary data, where we will have only 4 points we are taking. That is 0, 0, output is 0, 0, 1, output is 1, 1, 0, output is 1, 1, 1, output is 0. And we know, right, we have got these two red points. They are labeled as 1, and these 2 points, right, white, they are actually labeled as 0. And we cannot draw a line to separate them out. One thing we have to do, we have to draw some nonlinear boundary. You can draw something, a line here, another line here. Okay, so if you keep 2 nodes and one bias node in the hidden layer, right, in MLP it will work. Anyway, let us see if we can transfer. This is the input space, right? Now we are transferring this data, we are mapping this data from 2 dimension to 3 dimension. We'll introduce a new feature which is nothing but XY, right? This is a derived feature out of XY, okay? And if we can generate a new feature, these 3 features, X, Y, and XY, these 3 features can help us to transfer the data in 3 dimensions, where it becomes linearly separable. Let me explain in detail. X is 0, Y is 0, then what is the value of XY? We can multiply these two, we'll get 0, and we can generate this particular column together with XY. Now, let us consider this X axis as X1, Y as X2, and XY as X3, or in other words, not X, but Z, normally we say. It is Z1, Z2, and Z3. So this is our Z1, right? This is our Z2, and this is Z3. In 3 dimension, if we plot these points, 0, 0, 0. So earlier we had 0, 0, that remains here, right? 0, 1. Say 0, 1 is this point, and this point remains 0, 1, 0, right? So 0, 1, 0 is remain the same point. Now 1, 0, 1, 0, earlier we had 1, now it becomes 1, 0, 0. So 1, 0, 0, right? No Z axis, Z3. Now last point, 1, 1. Earlier the point was somewhere here, right? It was here, here. Now Z3, this axis is Z3, so this point moves to here, this place. So now always, you can always draw a plane, right? A plane separating these 2 points in one side, these 2 points in another side. Okay, actually this is the corner. You can think this point as a corner and a floor. This is one corner of the another in the same floor. This is another corner. This was in the other third corner, right? Opposite corner of this origin. But now it has gone up, right? At the higher. So you can always draw a plane across the room, you can say that. So it becomes linearly separable. Okay, you can draw always a plane that is linearly separable. Obviously, right? A plane is linear function. So it is possible. It is satisfying the Cover's theorem. Now let me give you, I have already talked about the other one, okay, that is there in my note. I'll tell that if the points are, say, some points are within very close to the 0, 0, and the other points are separated in 4 different corners, a quadrant, then you can transfer the data as x1 square, x2 square. You can map, and that it becomes linearly separable. Now, in this particular case, suppose we have the data into the input space, right? This is the input space, and as you can see that there is no line you can find to separate these 2 classes, right? So maybe this one will be there, and there will be one error, isn't it? But it is always possible to find a curved line like that, isn't it? You see that here we can get a very nice avenue, isn't it? With a very reasonable amount of margin, and we can find this particular boundary. Now this is the input space. Now we can always map this point using a transformation phi, right, to another space which is called the feature space, that may be in 2 dimension or maybe a higher dimensional space, where these points will map to this place, these points will map to this place, and we can find a line in the higher dimension. In picture it looks very simple, but in real life it is not so simple. Just to perceive something, it has been shown here. Okay, this is another example. These are the points which are not linearly separable. Now you transfer this point using some function phi, okay, where this point becomes phi of that. Every point is the image, okay, of all these points, and you see that is linearly separable. But again, this one is the input space, and this is in the feature space. And feature space is of higher dimension than the input space in practice, but it may be in the same dimension. Obviously, you cannot lower it down. Dimension cannot be lowered, and the data will be linearly separable. Okay, but problem is what this phi is. God knows, frankly speaking. But for the simple problems like say JOR and whatever data we have, in simple data, if we have, maybe looking at the data we can come up with. But there is no algorithm exist to find this mapping. However, there is another problem. Okay, now you see maybe this data is in say lower dimension, maybe in 10 dimension. Now there will be a very complicated curved line, right, separating these two classes. Now to transfer this data to find a particular feature space where it becomes linearly separable, maybe you have to transfer the data from 10 dimension to 100 dimension, right? Now you see in the 10 dimension we have to do some computation, especially if you see that we have to perform the dot product of 2 points, right? That what we have to feed to the QP solver, that quadratic programming solver, that is the dot product of two vectors together with their labels, right? We multiply it and we have to construct a very capital N by capital N, right? That those dot products, and to feed that to the QP solver to solve it, right? Coefficient of quadratic terms of alphas, right? So those things we have to calculate. So we have to calculate the dot product of vectors. Now in this dimension, it would have been done in 10 multiplication because it is 10 dimension. But if you transfer the data in 100 dimension, then it would be very difficult, right? Computation will be 10 times more because dot product calculation will be more. Okay, that is 100 dimension is okay, but if the data is so complex that you have to transfer the data into 1,000 dimension or maybe 1,000,000 dimension, so your computation will be very, very high. Okay, but in some cases, maybe you have to take the data to infinite dimension. Okay, and obviously then the computation is not possible. Now, there is one trick, one technique people have adapted called kernel trick that rescues this particular problem. Okay, and we will be discussing about this kernel trick. Now, I'll be describing that using my notes. Just I'll go here and then I'll be using my notes to explain that. Which one is this? Let me see. Okay, same thing. Hold on. I opened that. Where is it? No, not this one. Where is it? Yes. Okay. Can you see this?
Yes, sir.
Okay, just 1 second. Hold on. Let me go at the top. Okay. So I was talking about the other data, that is this one. Suppose we have got this input space, right? The data is somehow these negative points are very close to the origin, and the other data, the plus points are like this, right? Then it is easy to map this point from this particular space to another space, and mapping phi is phi x1 x2 equal to x1 square x2 square. Okay, then you see, suppose x1 square is the z1 axis, x2 square is the z2 axis. You map them, you print, you just put them in this particular space. You will be getting like this, and there is a line possible. So two examples you can see, right, that it is possible to transfer the data to one dimension to another dimension where it becomes linearly separable. And here is the example of the Zorn point. Okay, okay. There is some problem in the scanning. However, we can live with it. Okay. Now here you see that. What the problem now? We have got these points in input space xn, yn, and xn belongs to Rd in d dimension. Now here in this particular space, data is not linearly separable. Now we are transferring the data, we are mapping these data points to another space called Z, okay, which is a d dash dimension, and using this function phi. So the xn becomes phi of xn, which we can represent as Zn and label as the same, Zn yn. And what is Zn? Zn is equal to phi of xn. Okay, and n equal to 1 to capital N, while Z belongs to R d dash, that is d dash dimensional real space. And obviously, this d dash is greater than or equal to the d, and d dash may be infinity something. Okay. Now, what the problem will be? Now, what we will be doing is that we expect that this in the Z space the points are linearly separable. So here, what we have to work in the same way, then we can find the margin, and then ultimately the problem will be we have to minimize W half W transpose W, like the same subject to these constants, right? Yn W transpose Zn plus B greater than equal to 1. Now in this particular space, if we can find this W, so what would be our boundary? It is W transpose Z plus B equal to 0, right? Now you got a new point, say x star, because our point will be in the input space, x star. So you use phi to transfer the data to Z space, that is phi of x star, and then we'll get Z star. Once you get Z star, you put that point into W transpose Z star plus B. If it is greater than 0, then Z star will be in the plus class, otherwise it will be in the negative class. So you can label the x star in the plus if Z star is in plus, right? The label can be propagated to the input space. So that's how it is been conceptualized, you can say that. But there is one issue, right? We have to calculate W transpose Zn, isn't it? W transpose Z. Now, if Z is very, very high dimension, the dot product we have to calculate. Moreover, there are other issues also, and let's see how we can tackle that particular issue. And then we can construct the Lagrangian. This is the primal problem. We know that Lagrangian, we have learned how to construct it and how to solve it. So finally, we got this Lagrangian. Then we have written the dual. And how did we solve this dual problem for alpha? We have used a QP solver where we will feed the coefficients of these alphas, right? That is linear, no problem. Now, to feed this particular one, what we have done is we have to construct this particular matrix, isn't it? Now, to feed this matrix, let us see what we have to calculate. Okay, how can we get rid of this dot product, or is only dot product sufficient? If we can calculate the dot product of two vectors, is that then will it serve our purpose? And if it's possible, can we find a trick or technique to calculate the dot product in an easier way? That is the main objective now. So linear coefficients are 1 and quadratic coefficients there is 1 minus half into this, right? Now you see here what we are calculating is ym, right? There are ym, or whatever it is. If you see that these are the levels, either plus 1 or minus 1, we can multiply easily. What about the other term? That is the dot product of two vectors in the feature space, in the Z space, right? Now, if Z is very high dimension, obviously this complexity will be higher. Now, what is that high? Is it 100 dimension? Is it 1000 dimension? Is it million, or is it billion or trillion? Or maybe it is infinity, right? Obviously, the complexity is higher. However, what we can see is that to use the QP solver, if we can calculate this dot product somehow, then we can obviously feed this data to QP solver and we can get the values of alphas, right? The Lagrange multipliers. And once we get the values of alphas, a few alphas will be positive. Those are the support vectors. We know that. And that's what our objective is. So dot product is sufficient to find the values of alpha, right? That means to find the values of the SVMs. That's fine. Okay. Now, once we find these values of alphas, can we find the value of W, right? The weights. Let's see what is the value of weight. The W is equal to, we know that is n equal to 1 to capital N, alpha and y and zn, and most of the alphas are 0. So it would be actually the you are multiplying only the support vectors, right? If you have say 1, 2, 3, there are 3 support vectors for simplicity, then it would be alpha 1, y1, z1 plus alpha 2, y2, z2, alpha 3, y3, z3. Okay, only this one we have to do. Okay, now here you see W equal to this, right? Now, do we need to find this W explicitly? Okay, why do you need to find the W? We need to find the W to find out whether a point, right, where it belongs to. Now, instead of finding W explicitly, what is the equation of the boundary? W transpose Z plus B. And another thing, how do you classify or how do you predict in which class a particular point, say Z, belongs to? You put this point Z within this equation, unknown point Z, into this W transpose Z plus B, this expression. If this expression is greater than 0, then we classify that point in the plus class. If W transpose Z plus B is negative, we'll do that. Now, this is fine. This summation expression is there. But can we avoid to find explicit value of W? Let's see. Now you see, you have got a point Z, which is unknown. It is there. And what value you have to calculate? You have to calculate the value of W transpose Z plus B. Now replace this W by this one. Okay. You see what it becomes. It becomes n equal to 1 to capital N, alpha and yn, Zn transpose Z plus B. Now you see alpha n we know, we have already calculated, right, using QP solver. Yn, the level of the nth point, all the levels of all the existing, right, training samples. Zn is the training sample points or maybe the support vectors, and the Z, right? That means you are calculating the dot product of the support vectors with the unknown point Z. Okay, now if we can find the dot product, so this is nothing but the dot product, right? So we do not need explicit W. What we need that the dot product of the support vectors with the unknown point Z. Then we will be able to find the value of this term at least. So I will come to the point B, right? So this is fine. So far, to predict the class of an unknown point, right? What we have seen, we can calculate the support vectors by calculating only the dot product. So if we can calculate the dot product, it is sufficient. Okay. In fact, to find out the class of the unknown point, we do not need the explicit value of W, but what we can do, we can calculate the dot product of the unknown vectors with the support vectors, then we can do it. How about this B, right? Will it spoil? Let's see how we can find the value of B. Now you see, if we have a support vector Z1, right, we know, then obviously we know Y1 into W transpose Z1 plus B equal to 1. We know that, right? It will satisfy this condition. Now, if we satisfy this, we know what the value of W, that is alpha and Y and Zn transpose Z1, and we know Y1. So this will be an equation, and if you can solve this equation, we can find the value of B easily. And what this equation contains? It contains only the dot product again. Here the dot product of the support vectors with the one support vector only, right? So Z1 is support vector, and there are say other support vector with Z1, Z2, Z3. You can do the dot product, and from this equation you can find the value of B. Right? Now, once you can find the value of B, now what we can conclude then is that we do not need to bother about what the W is, right? We do not need the explicit value of W. Instead, if we can find somehow the dot product of two vectors in the transfer space, that is sufficient. One more thing. Do we need the explicit representation of Z? It is not necessarily. Okay? Because you have something, okay, you have a point in the X space, you are transferring the point into the higher space, right, phi, and you will be wondering, then how shall I see the Z, right? There is some transformation phi we are giving. Now, can we avoid to find explicitly the point Z? Okay, can we avoid that? Then it is easy. And if we can avoid that, then it would be easy for us to actually simplify this particular method. However, what we need, we do not need what Z is, but what we need, the dot product of two vectors or two Z's actually in the transfer space. You have the points in two dimension. Maybe you are taking the point in higher dimension, and there where the data becomes linearly separable. Now, whenever you are mapping the points from 2 dimension to 100 dimension, so there has to be a function, right? Phi, the transformation, what it is, whatever it is, the complicated functions of X. Now, instead of explicit point, where does it lie? How does it look? We do not need to bother about that. What we need, you take a point here, you give a transformation, you have another point here, you give it that point, you transfer that point also in the Z space. There will be Z1, Z2. Here you had X1, X2. There it is Z1, Z2. You do not need to bother about how Z1, Z2 looks like, but what you need is that the dot product of Z1 and Z2 only in that space. So you do not need to know the explicit representation of Z1 and Z2, right? But what you need is that the dot product of Z1, Z2 only, right? Because then that will serve our purpose. Okay, so if we can find the dot product of two vectors in the Z space, that is all right. We do not need anything else. Therefore, we may not need to find Z equal to phi X. That means we do not need to look how this Z looks like. Like in the example, right? We had a point X1, X2 in 2 dimension. We have transferred the point as X1 squared, X2 squared. So we know, right? That is we can perceive it, we can feel it, and we know we can draw it if required. Say for the XOR problem, we had 0.00011011. Now we have given a transformation into the 3 dimension. What those points are? 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, and 1, 1, 1, right? The third coordinate, we have third dimension, right? Third component we have introduced, that is the product of these two. So we are transferring a point, the phi, right? That x1, x2 to x1, x2, and x1, x2. That transformation, we can feel it, so we are very strong, right? It is easy for us to perceive. But doesn't matter, there may be a very complicated function of 100 dimension. Okay, but you do not need to bother about how does it look like. You have a point x1, you transfer it. You have a point x2.
Are you in the same page? Are you in the same page, or you have moved to somewhere else?
Sorry?
Are you in the same page?
Same page means no, we are not in the same space. We will be transferring to
another. In terms of your slide, whether you have moved to some slide or you are still in the handwritten page. Okay, fine.
Okay. Can you see this?
Yeah.
For example, the page number 4.
Oh, right.
Yeah, here it is. This is just conceptually I'm talking about. Here it is only. No problem. Okay. So this is just conceptually I'm trying to convince you that we do not need to bother about how the transferred points looks like, right? What we need to bother about is that you transfer couple of points from your input space to your feature space, and if you can calculate the dot product in the feature space, that would serve our purpose. Okay, that's what I am trying to say, because what I earlier said is that to solve this dual problem, what we have to calculate is these coefficients, right? And what you need is only the dot product of two vectors in the feature space, and then to calculate the W, this is the function, but we do not need to calculate W explicitly, but to find out the class or to predict the class of an unknown point, what you need to calculate the dot product of the unknown point together with the support vectors, right? And to find the B also, if we can find the dot product, that will serve our purpose. Okay. Now, if you have a mechanism, therefore we may not find z equal to phi x. Instead, we need the dot product or the scalar product of vectors in the z space. Okay. How about a mechanism that takes xm xn as input and provide us zm dot zm? That means you can find a technique that will take xm and xn as an input, and you will get the dot product of two vectors in the transfer space. Because to use SVM effectively, to classify the data, what computation you need? What you need is that you have 2 points, x1, x2, and then Swarup is waiting somewhere. I will pass the point to Swarup. Okay, if Swarup, you take x1, x2. So Swarup does something. Okay, he takes the points to the Z space, and then he can compute the dot product of Z1, Z2, and return us the dot product of Z1, Z2. Now, what this Z1 is, what this Z2 is, how does he calculate this Z1 dot Z2? I do not need to bother, because what I bother about that the dot product of two vectors in the transfer space, and how Swarup will take the point to the Z space. How does he calculate the dot product? That I do not need to bother. So we can think of that a black box, and we will feed two vectors in the input space. In the input space, we have got two vectors, maybe xm and another one is xn, and we'll feed those xm and xn. This black box will take the point into the higher dimension, that may be infinite dimension, and here the dot and that black box will compute the dot product of two vectors in the infinite dimension and return us back, right? You understand? So you can think of like this, that suppose, I like eating and I like to eat or something like that. That's why my examples are like that. Suppose I like to eat mutton curry, okay? But the ingredient I have is the potato and maybe say pumpkin, okay? Now there is a box. I just put pumpkin and potato with some spices I have. I put inside the box. I close it. Say after half an hour, I open the box and I bring out the mutton curry. This is like that. You understand? So this is a mechanism. There is a mechanism. What we expect? What we expect is that we will feed pumpkin and potato, and that particular black box will return me the mutton curry. That's what we are expecting here. What we are expecting, a mechanism that would take xm and xn, the points in the input space, and that particular mechanism will take the point into the higher dimension, if required maybe in the infinite dimension, and it will calculate the dot product of two vectors and return us the output. That's mechanism, okay? And that is available for this kernel function, okay? So this is a box. It is taking xm and xn, and the output is zm zn. What is zm? Zm is equal to phi of xm, zn equal to phi of xm. And zm zn are the points in the feature space corresponding to xm xn. Now, what this zm is, what this zn is, we do not need to bother, because we do not need. The mathematics, whatever we have seen, this dot product of two vectors is sufficient for us. If we can calculate the dot product of two vectors, that would be sufficient. We do not need to explicitly know how those points look like. Correct? Now, this K, this black box, right? There was a concept called kernel function. Now, kernel function comes to the rescue. Now, here there is a function we will discuss now that will take 2 points. This function will, the output will be the dot product of two vectors in the transfer space. Okay, the transfer space may be a higher dimensional space, or if required, obviously it is required, right? Whatever is required, it may be from xn, xn are in 2 dimension, or maybe a single dimension. Then Zm may be 6 dimension, maybe 100 dimension, maybe 1000 dimension, maybe million, billion, trillion, whatever is required. If required, we can take the point into the infinite space. You know, right? The calculation of dot product of in infinite dimension is not possible. But this kernel function actually does that. This is a magic, I can say. This is a magic function, you can say, right? As I said, that you feed pumpkin to this guy, and this guy will return you mutton curry. You understand that, right? So it is so cheap also. See, if you have to perform the dot product in 1000 dimension, you have to multiply, complexity is 1000, right? Now, but in infinite, it is infinite computation. It is not possible. However, we can get the benefit of infinite dimension using this function, where the computation may be just, if the xn, xn are in maybe say 2 dimension, maybe here you have to go up to 3 or 4 product. You understand? So you increase little bit, very little bit of, your cost will be increased very little bit, but you will get advantage of very, very high level, a huge advantage. Okay? These kernel functions provide us. And this is possible to apply these kernel functions because I tried to explain in the beginning, what we need only the dot product of two vectors in the transform. We do not need to bother about the exact existence of this point or even how does it look like. We do not need. What we need, the existence of this dot product only. Okay? Now, how does it work? Okay, Swarup, is it clear now? that what I'm trying to say is that so far whatever we have seen, what we need is that only the dot product, right? We do not need the explicit
Exact.
exact point, right? Okay. Now I'll give some kernel function now, and now please go ahead and tell me whether you could able to understand something, whatever I try to convey. Hmm?
No,
Yes, hello, go ahead.
no. Can you repeat and what you asked?
No, what I am trying to say is that we have learned linear SVM, right? Explicitly.
Right. Right.
There was no problem for us to view it.
Right.
Now, in the nonlinear, we are talking about some abstract stuff, right? That we are taking the points in the higher dimension, we are mapping the points, right, using some function phi. And again, I'm telling, we do not need to bother about what that phi looks like, those points looks like, and whether they exist or not. But what we want, that we'll feed something 2 points, and we'll take the point into higher dimension, we'll calculate the dot product and come back, right? So dot product is sufficient. That is clear, right now?
Right.
Yes. Okay. Now I'll give some kernels examples. And yesterday, I think someone, Binan or somebody was asked saying, right? He has studied, and there is some very famous kernel called RBF, radial basis function. I'll come to that point as well. Okay. Now, what this kernel is? Kernel k dot dot, two inputs we have to give, helps us to get the dot product of two vectors in Z space. However, we do not need to find the individual images, right? That's what again and again I'm trying to say. Now there is one kernel example. Maybe the scanning was problem. However, we can live with it. Suppose we have a point x in 2 dimension. X space is in 2 dimension. We have got x1, x2, two components. And phi is a mapping x to z space, where x belongs to R2, right? 2-dimensional real space, and z is 6-dimensional real space. So I'm trying to design a kernel that would take our points in 2 dimension as input and take these points into 6-dimensional space, calculate the dot product, and provide us the output. Okay, it is a simple kernel called quadratic kernel, and let's see how does it work. Okay, just I'll show you the inside. We do not need to know actually inside though, but we will be using that kernel function and it will work. But we have to somehow perceive it. We have to understand actually that particular kernel function is taking us or taking the points in 2 dimension, right, to the 6-dimensional space and calculating the dot product and giving us the dot product, returning us the value. Okay, I'll just demonstrate that one. Now let us think about a mapping like this. Say Z, a point x. Okay, x is a point which is x1, x2. Phi is the mapping, and this is the mapping I have designed. We are taking a quadratic mapping. This, forget about this constants √2 time being. Actually, since I would have written, I would not have written this, but quadratic transformation. If you have a 2-dimensional point, the quadratic terms, there will be a constant term. There will be x1 square, there will be x2 square, there will be two linear terms, x1, x2, and there will be x1, x2, right? So x1 square, x2 square, x1, x2. These are the three quadratic terms. There will be two linear terms, x1, x2, and 1. So what are the terms in the 2-dimensional quadratic expression? That is x square plus y. X square we have, y square we will be having, x, y we will be having. We will have x, we will have y, we will have a constant term, right? We know that very well. That is the normal general function of two dimension is ax square plus by square plus 2hxy plus 2gx plus 2fy plus c equal to 0. This is very much familiar we are, right, in analytical geometry, and we know, right, in what condition it is a circle, in what condition it is a pair of straight line, when it is parabola, and all those things we are very much familiar with. So in two dimension, there will be three quadratic terms, two linear terms, one constant term. And this is the transformation I am given. Now there is another point, x dash. This is x1 dash and x2 dash. The same mapping we have to perform here. This is constant term, x1 dash square, x2 dash square, x1 dash, x2 dash, and x1 dash, x2 dash. These are the two transformations we got. Now you see x, this is in two dimension, right? X dash, this is also in two dimension. So we are mapping x dash, two dimension to, here it is six dimension, obviously, right? Constant also is another dimension. Now perform the dot product of this z and z dash. Z and z dash, what is the dot product? 1 into 1 plus x1 square, x1 dash square, x2 square, x2 dash square. Root 2, this x, it would be x1 and x1 dash, right? There will be x2, x2 dash, x1, x2 into x1 dash, x2 dash, right? These things. Now, just to write these as a whole square, we added actually some constant terms here, right? Some we can always add some constant here, root 2, root 2, root 2, root 2, and root 2, root 2. You know the main objective is, so that it becomes 2x1, x1 dash, 2x2, x2 dash. Here also 2x1, x2, x1 dash, x2 dash. Now, what is this? This is nothing but, you see, 1 plus x1, x1 dash, x2, x2 dash whole square, right? Now you see, what is this two terms? That is nothing but x dot x dash, right? So this is equal to 1 plus x dot x dash whole square. Now you see, I'll come back again. We had 2 points x and x dash in two dimensions. We have given a transformation phi, obviously, right? The transformation, this is a very well designed, well thought of transformation, but this transformation taking us from 2 dimension to 6 dimension. We have given the transformation phi to x, we have given the transformation phi to x dash, and then we perform the dot product of them. We have got this, which is nothing but the dot product of two 6-dimensional vectors, and that is nothing but this one. Now you tell me, how long does it take to compute? You compute the dot product of x and x dash, right, in the input space, and you perform a square. To perform a square, little bit of extra computation you are doing, but you are getting the advantage of 6-dimensional space, right? To calculate this dot product, you have to perform 6 multiplication, which will be to calculate the square, right? There will be 2 multiplication together with the square, maybe another 1 multiplication, 3 multiplication we can do it just for the square. This is the quadratic kernel, okay? So this is the kernel. So k, this kernel is x comma x dash, these are the inputs, and this is the function you use. Okay, so we do not need to bother about how do they look like, but this is a quadratic kernel. So we can now go for q degree polynomial. So you are saying, no, actually the data, whatever we got, if we just transfer the data in 6 dimension, use quadratic kernel, it will not work. I have to take maybe say 10 degree polynomial. You know that, right? 10 degree polynomial will be having, say, I can tell you 10 plus 3 minus 12c2 terms. And 12c2 terms is huge, right? That is 12 into 11 by 2, right? So 66 terms. Now we are not happy with that. Okay, you take the point in 100 dimension. In the 100 dimension, it will be 100, 2 into 101, 101, yes. So it will be huge, right? Almost 10,000 terms, right? 10,000 dimension points. So now q degree polynomial, this is the polynomial kernel, okay? And these are the terms we will have. In the q degree term, the phi x, we can write as, there will be a constant term, and taking the point in 2 dimension only. There will be linear terms, there will be square terms, there will be cubic terms. Ultimately, the general term is this, right? x1 to the power r minus I, x2 to the power I, isn't it? And r will be equal to q. We know that. So summation. So what we can write as this one. Okay. So what we can multiply here is a constant term, QCR RCI. So this is the one we have done. So Z is this transformation, R equal to 0 and I equal to 0 to R. This is a huge number of terms, right? Depending on the Q. So you transfer Z dash also, then you multiply each term. Okay, it would be summation of this term. What is that? QCR RCI, x1 to the power r minus I, x1 dash to the power r minus I, x2 to the power I, x2 dash to the power I. Okay, so you can correctly guess what it is. This is nothing but 1 plus x1 dash plus x2 dash whole to the power q. Okay, this is what is this expression? This expression is this QCR into this, and it is the same. Okay, so we can write this way. You see, this is how we have written this dot this. Okay, so what we can do, that k of x dash equal to 1 plus dot product of x. This is, there is 2 multiplication and to the power q, right? And to perform to the power q exponential, obviously we do not need to do that. Say q, it's very huge, right? Multiplication. Little bit extra computation is giving us the advantage of a higher dimensional space. So this is another kernel, very popular kernel. Okay, q degree polynomial kernel. Okay, so you can feel it, right? Slowly that, okay, this is the function, kernel function that is taking the point into a very high dimension. Actually, this will be q plus 3c2, q plus 3 minus 1. So q plus 2c2, q plus 2c2. If q is high, you know, right? Q plus 2c2 is very high. So it will be very high, this one. Now, instead of q, there are several other kernels, but you are not happy with this. Okay, you may have to take the point into infinite dimension and do that. And for that, I'll discuss about this RBF kernel. This is the most popularly used, most popular rather, and most used kernel, and it has got a very nice characteristics as well in the k-means and all those things in machine learning. This RBF is very famous function. We didn't have opportunity to discuss about this function, but later, if possible, we'll do that. Anyway, so RBF kernel looks like this. Okay, kx dash equal to e to the power minus gamma norm of x minus x dash whole square. You know, norm we are familiar with now, right? Magnitude of x, the vector x minus x dash. Very simple. And gamma is obviously some greater than 0. Now, I'll demonstrate it that x and x dash in single dimension, because frankly speaking, to demonstrate it, to write down here, right, or to explain it in 2 dimension, it would be a bit complicated. So it is advantage, right, for me being a teacher. We can say that take the example in the easy one, simple example, and leave the complex for the students. But anyway, you can do it. I also can do it, but we do not need to do it in this particular lecture. Let's see what it is. We have got, say, 2 points in 1 dimension only. 1 point is x and x dash, and I will show you how this kernel, this RBF kernel, help us to take this 1-dimensional point into infinite dimension, compute their dot product, and return us, okay, the value. So x1 belongs to R1. Now let's see. What is the norm of x minus x dash? That is very easy. X minus x dash whole square, right? Simple. So it is minus gamma, x minus x dash whole square. Okay. Now what is this? So it is e to the power minus gamma into x square plus x dash square minus 2x x dash. Now what I am showing that this is nothing but dot product of 2 infinite dimensional vectors. That's what I'm going to demonstrate. So we are taking these points in 1 dimension, to the infinite dimensional space, calculating their dot product and returning us this particular function. Okay. So this is the one. Now I have to break it down. What is this? This is e to the power minus gamma x square into e to the power minus gamma x dash square, and then e to the power minus minus plus 2 gamma x x dash. Okay, that's what we got. Now let's see. This is e to the power minus gamma x square. You keep it. This one also keep it. And what about this term? Right? We know the expansion of e to the power x. That is 1 plus x square by factorial 2 plus x to the factorial 3, like that. And that is nothing but this one, right? R equal to 0 to infinity. This term to the power r by factorial r. Now what we can write? To take the x's one side and x dashed in the other side. E to the power gamma x square, and take here. What is there? X to the power r by factorial r, right? X to the power r by factorial r will be there. And there will be 2 gamma. So 2 gamma by factorial r, right? 2 gamma by factorial r, we have split into 2 sides. Square root of this here, and other part with, it goes with the x dashed. So e to the power minus gamma x square into x to the power r, right? And here e to the power minus gamma x dash square into x dash to the power r. The other term, 2 gamma by factorial r, 2 gamma to the power r by factorial r, is split into 2 parts. One is square root of this side, another square root is here. Now you see, this expression is nothing but this one. What is this one? If you see this, if you write down, that is z equal to phi x, you take this e to the power minus gamma x square, you put r equal to 0, you will get 1. R equal to 1, you put 2 gamma by factorial 1 into x. You guys put r equal to 2, you will get 2 gamma to the power 2 by factorial 2 square root of that into x square. So we can write down the whole thing. And what is this dimension? This is infinite, right? Infinite terms will be there, isn't it? E to the power x. So z equal to this. So we are taking a point x into infinite dimension like this, and we are calculating, we are taking x dashed into infinite dimension, then computing the dot product of these two vectors. Okay, so this RBF kernel, okay, always help you to take the points into the infinite dimension and compute the dot product and provide us. And as you see, the computation of this one, right? Obviously, to calculate the norm, we have to calculate the product of, say, d dimensionals. If the x is in d dimension, input space is in d dimension, so there will be d multiplication. And there will be some square, there will be a multiplication here, and you have to take the exponent of that. To compute this one, maybe little bit of extra computation we are performing, but we are getting the advantage, right? To take the point in infinite dimension and work in infinite space. And infinite space, everything goes to the linearly separable. But only thing is that we have to be very careful about this gamma, okay, and these kernels, because it is not necessarily that always you just feed the data and you select one kernel, it will work. This is not necessarily, right? As you anticipate correctly, that it is not always possible to take the data in some other space and so that it becomes linearly separate. You have to be very, very careful to selecting the data, isn't it? So, or that particular transformation. And actually this kernel is helping us to take the point in our desired space, and we do not know what the desired space is. But at the same time, it is calculating the dot product and giving us. So two things it is doing in one space. But you have to be very, very careful about selecting this kernel. Sometimes maybe this quadratic kernel will work. Sometimes maybe this some 10-degree polynomial kernel will work. And there may be, say, RBF kernel. There are hundreds of other kernels. You can design your own kernels. There are a lot of references in my presentation toward the end, or you can give a search in the Google and you will get a lot of references of RBF kernel. Okay, now problem is you have to select the appropriate kernel. And nowadays in industry, if someone say learned how to use the tools. They will feed the data, they will use one particular function with some default parameters. If it works, they will say, oh, I have done it, right? I know machine learning and all those stuff. But if it does not work, no, they do not know how to correct it. Another problem is that this use of SVM, right? To me personally, if you give a problem, I will not go for SVM in the beginning, frankly speaking. I never go for that. I never actually used SVM in the beginning, frankly speaking. Say I get a lot of industries project, okay, industries data. When those people say they use all the tools and they could not able to reach the appropriate result, or they didn't get the result, then they contact us, right? That you see, we got the data, can you do something? Then I do that, okay, you use this, you use that. They say, no, we have used it, it didn't work. Then I take the data, I work on it, and I use appropriate parameters, and I analyze the data, somehow it works. You know the differences, right? But frankly speaking, I never tried SVM in the beginning as well, because it is very, very difficult to select the appropriate kernel, because in real life you will get always non-linearly separable data, right? It is not so simple. So it is really, really difficult to select the appropriate kernel. Actually, I prefer neural network because it is easy to understand, at least for me, right? How neural network works, what the impact of the parameters and all those things. But it is very difficult to view this SVM. Okay, actually, Yasser Abu Mustafa has correctly explained it. What he said, that maybe, say you are sitting in Gangtok, okay, the Sikkim University campus, and you have to travel to Calcutta. So there are three different options. You have got a car, right? There is another option. You can purchase a, or maybe you have purchased a plane ticket. You have to come to the airport, Bagdogra, and then you have to come here, right? But you know how to drive a car, but you do not know how to drive a plane. So you cannot, suppose there is a plane is lying, but there is no one to take it to the Calcutta, right? So, but you have to know how to drive a plane, right? How to use a plane. And another thing, even if you do not know how to drive a car, right? Even if car is lying, you cannot use it. There may be a there is another example. Say we buy hi-fi smartphones nowadays. Now there are people who buy very expensive phones, but they do not know how to use the different several features of the phone. They just call it, like myself, frankly speaking. I use phones just to call people, and nowadays little bit of say WhatsApp maybe, or these are watching videos, like listening lectures like that. But there are several other features existing, right? And my son bought one Apple phone for me, an iPhone. So I'm not using it. So you may have a very good machine, but you have to know how to drive it, frankly speaking. So what I say, SVM is a fantastic machine, very powerful machine, but you have to know how to use it. That's why my suggestion would be that, okay, you do it, then you learn it in detail, you practice it, then you use it. Nowadays, actually, slowly I'm gathering some experience, okay, knowledge about SVM, and I am using it. Now, use of SVM depends on the appropriate use of kernel. Okay. Now, can any function work as a kernel? Validity of kernel? No. Say you use a kernel, it works, so you go ahead with that. But there is another one. If you have a data set, you select a kernel, then you can check whether this kernel works or not. There is a validity of a kernel. Okay. And the validity is like this. For a given data set, xn, yn, let z phi x is a transformation zn, yn, and this is the dual. Okay. Now here, this is the input matrix we have calculated. You remember this? Z1, Z1, Z1 transpose Z2. You calculate this matrix. There is one theorem called Mercer's theorem, MERCER. Have I written? Yes. Mercer's condition. A function, a kernel, a kernel. Where do you use kernel to calculate this? This one, right? All the dot products. That is the kernel. So you can use this kernel to calculate, to compute this matrix, which we feed to the QP solver. Now, this matrix, what would be the dimension of this matrix? If you have n number of data, it will be n by n. And to compute all these dot products, you use your kernel. Now, this K is a valid kernel for the given set of data if this function is symmetric, K, that means Kxmxn is equal to Kxnxm. Okay, as I said, right, that square, the norm square, that is symmetric, isn't it? So this type of, it has to be symmetric, and this function has to be positive semi-definite matrix. Okay, that means non-negative definite matrix. Positive semi-definite matrix means one way to calculate, to find out that all the eigenvalues of this matrix are greater than or equal to 0. Okay, so if it satisfies, then this kernel is a valid kernel for the data set you got. Okay, that is called the Mercer's condition. Mercer is a very famous mathematician, okay, contemporary or maybe a bit senior to Einstein. Okay, so there is one Mercer's road in Princeton and all those stuff. Anyway, there are a lot of stories about it. He's a very famous mathematician. He has given these conditions, Mercer's condition. Q is symmetric. Okay, Q has to be symmetric if this is symmetric, and Q is positive semi-definite matrix. Okay, so this is about kernel and nonlinearity. So just to summarize this, we are not finding out a curve, right? Instead, we are taking the point into the higher dimensional space with the expectation that in that space, data becomes linearly separable. Okay, now that's fine. We'll take the points. We may not need to find the existence or how does it look like, but what we need, you take the points there, that's fine, and calculate the dot product, and if we can get the dot product of two vectors of that space, that will serve our purpose, right? Because of the unfortunate expressions, right? Whatever we got of this Vepnik and Chebronenkis computations, right? The expression, whatever we got. And we have got QP solver, and that provides us all the benefits. This is what I wanted to say, okay, about this SVM. Now I'll stop this presentation, okay, and we'll come back to the other one. And there are a few more slides in my presentation. You can go through that, and there is one problem also solved, okay, one numericals. So you can look at that too, so that you can get a better concept about this one. Okay. Now, right now I will not take any question. Maybe it would have been good for me to take a say 5-10 minutes break. I think I will take it because I will not take much time in the DNN, deep neural network. Okay, I'll just go to the washroom in 10 minutes and take some water and come back. Sarup, is that okay?
Absolutely, no problem.
Please, because I am talking so much. And in the meantime, you think about it, application concept. Can you see this?
Yes.
Okay. Anyway, these are, I have already talked about all those things. There are many things. You can have a look. And okay, I was telling that now people, what they are trying to learn the pattern, right? The way one artist used to draw the pictures or paint the pictures, and then if something new come up, like Mona Lisa, right? Leonardo da Vinci's painting, would have been painted by different famous painters, artists. How do they look like? One of them is I do not know which one is. This maybe Picasso. One is Vincent Gogh. Another one is Paul Gauguin. Okay, if they would have painted Mona Lisa, how would it have been look like? We know these are not painted by Leonardo da Vinci. This is the one. Okay, in 2018, $500,000 painted by a machine. Okay, then Netflix is a very famous one. This is a simple machine learning example. Normally we talk in the beginning. Actually, this is a presentation I presented in one of the in one centenary was there one institute. So they invited me to talk. So we talked about this. So these are the basic things. What is machine learning? Then what is learning? In my understanding, I tried to explain. Anyway, so I'll go to the deep learning. Okay. You see, in the deep learning, what they do is there is some basic information. Say whenever say we go for say face recognition, right? Recognizing face is very complex. It's not easy, and surprisingly, the human being has a very what shall I say? Very complex mechanism to identify a face. So if you might have studied with thousands of your friends, right, in school. Now after maybe 10, 15, 20 years later, if you just meet them, you are able to identify them. At least if you are not able to identify them by name, you can see that okay, you have seen them in a school, right? That's what you feel it. So like that, in deep neural network, in the face recognition, what is the input to a machine? It is nothing but the gray level image. And machine obviously cannot view, unlike a human being, all the pixels in a simultaneous way, right? In one shot. The machine has to take one pixel by one, right? So these are the basic concepts. What they try to do, they somehow try to extract the simpler concepts. These are the low level features. If we consider these as low level features, then this is a bit higher level, simpler features, but not very complicated. They convolute rather. They mix a few pixels and then they generate some low level features. Then from low level features to high level feature, and finally they got a meaningful feature that will help us to identify something. It's like eye, mouth, nose, right? These are different parts of our face, and from the low level, say a particular area, right? They are the pixels, and then you identify different, maybe say one is nose, one is that, and all those things. Maybe nose are existing in several living beings, animals, and how these nose, eyes are combined together, right? We can view as a face of a person, and obviously for different persons. So main concept is that in the deep learning, we feed the low level features. From the low level features, it generates some high level features. Finally, the feature which helps the machine to identify. Surprisingly, these features, okay, finally, this is the final concepts, right? That will be explicitly a feature that would help the machine to identify. But those features may not be recognizable by a human being as well. Okay, so does not matter. If machine can use them to recognize a person, that is enough, right? So this is the one. This is a deep graph. See, deep learning is same as learning. Only thing is that it is a bit complex network, you can say that. Architecture, learning mechanism, whatever it is, I normally explain. So here are some deep learning examples. Multi-layer perceptron with a huge number of nodes and huge number of layers. That is also considered as a deep learning, deep neural network. Then we have got convolution neural network, recurrent neural network, GAN, several other other network models are also there for the deep learning concept. Okay. Now, all these things came up or devised, you can say, to handle different type of problems. Say for multi-layer perceptron, you have got here only 4 I'm demonstrating. It may be say millions of nodes maybe you have got, or maybe thousands at least. If there are thousands, it should be 100. Maybe it will increase and then again it will be same. Maybe three outputs, right? 3 classes or maybe something like that. So this is a deep neural network example that in the multi-layer perceptron, see, this is a complete, right? You feed the whole thing, then all these weights, right? We have to learn. There will be many connections. We know that, right? Number of connections we can compute, and you see that there are many connections, fully connected layer, fully connected networks. So this is a huge amount of weights, and obviously it is we can always feed even an image to MLP. Now if you have an image, say 1024 by 1024, so you have to have 1024 into 101 million nodes in the input layer itself. If you have 1 million, obviously this will be much more. The connections will be huge, right? Maybe 1 trillion, not more than billion, right? Number of weights, and obviously it is time consuming. Now, if the image is not a gray level, but a color image, then it would be 1024 by 1024 by 3, right? So it would be more than 3 million nodes in the input layer. So it would be huge amount of weights, and it will take maybe months to train this particular network. It is not work. Instead, can we reduce the number of weights so that learning will be faster? And that's why people came up with a concept called CNN. I'm not talking about this word to vector. You can see word to vector concept. This is the CNN. I'll talk about that. CNN is a very famous concept, convolutional neural network. Okay. And in this particular convolutional network, there are quite a number of layers. You will see that. There is a convolution layer. I'll discuss about what is convolution layer. There is a ReLU, rectified linear unit. Okay, that is a non-linear transformation, whatever it is. Actually, these convolution layers, they will take the low-level features and they will generate a set of features, feature map, they call it. Okay, there is a name of this, what they call these activation maps. Okay, there will be activation maps, there will be another further activation map, and there will be a pooling layer. Okay, there are several pooling concept is there, one pooling layer, I'll explain that. And then again convolution layer together with this ReLU, and then pooling layer. So this type of repetition, right, will be there. Finally, if you have say maybe 1024 by 1024 here, finally it will come down. It is not 3, right? There are 6 convolution layer here and 3 pooling layer. Nowadays, there are convolution layers. There we may have say more than 500 convolution layers. So after 500 convolution layers, finally these activation maps will be very small. Maybe it will become say maybe 16 by 16. So only 64 will be there, and then we attach a fully connected layer, okay, to identify different objects. Okay, so here it is 1024 by 1024 by 3 color image, and then finally we are getting here maybe 16 by 16 by 10. Okay, in the fully connected, so 16 by 16, 640, one fully connected, there is not many weight. 640 into maybe say here 5, so 640 into 5 is reasonable. It will not take much time to learn. But here, can you reduce the number of weights or parameters? That is the primary objective. So this is an example, a simple example, simple CNN presentation. Now, what is convolution layer? Now, for example, I have taken here a simple image input, which is 32 by 32, and it is a color image, right? The depth will be 3. This is called depth. So you have got height, width, and depth. So it is nothing but we can consider it as a 3 images, right? 3 two-dimensional images you are feeding. RGB, the 3 components, right? Each pixel will have. So this is 32 by 32 by 3. Then what we do, we take a filter, maybe 5 by 5 by 3, because their depth is 3, right? So you put this filter somehow here, and this filter will help us to convolute here 5 by 5 by 3. There is a, in each image, right, there will be a 5 by 5 window and depth 3. So there will be, say, here how many parameters? 5 by 5 by 3, 75. Maybe say W11, W12, W13, W14, W15, W21, W22. There will be weights associated with each point in the filter, and that will be multiplied with these image components. So we can perform the dot product and we will produce one value. So 5 by 5 by 3 into this filter, part of this image into this filter will produce one. Then you shift this one little bit, maybe 1 pixel, right? You shift in the right side, then you again right side, again go. So there will be how many? Here it is 32 by 32. So here 2 will be deducted. Here also 2 will be deducted. So it will become 28 by 28, right? So it will generate 28 by 28 two-dimensional matrix. If you go through this filter and just pass on this filter, slide over the image, specially computing dot products. This is like this. So this is the pixel, this is the filter, or another name of this filter is kernel. So here it is 32 by 32. You use this filter, slide over this filter over the image, but just what you are sliding, you are taking one step only. It is not necessarily that it is one step. You can take 2 steps as well, or maybe 3 steps if you want. That is called stride, S-T-R-I-D-E, stride 1. Stride 1 means you shift only one cell in the right side and as well as in the bottom. Okay, so if you just do that, convolve over all special locations, and it will generate one activation map. Now you take another such filter and you can generate another activation map. So here 2 filters of size 5 by 5 by 3 will generate 2 activation maps of 28 by 28 by 1. Normally we take maybe number of such filters. These filters actually will try to extract different types of features exist in an image. Maybe one filter will help us to identify the vertical lines, another one maybe horizontal line, another maybe contour or something like that. So you can take different types of filters to constitute or to find out, to extract the bit higher level feature that is called activation maps. They are called activation maps. So this is the work job of the convolution layer. Now there is a ReLU layer. ReLU layer is neurons that applies the activation function f is equal to not a max of this. This is 1. This is the pooling layer. Also we can do that. Otherwise we use say something like whatever we have sigmoidal function or tan hyperbolic function. We do that. That is the nonlinear transformation we are giving. Okay, that is the ReLU. Normally we are familiar with that. And then you do say here we have gotten 32 by 32 by image. We took 6 5 by 5 by 3 filters. So how many activation maps we will get? We will get 6 activation maps. And since we have taken stride 1, we are shifting only one cell. So we will get 28 by 28 by 6. Okay. Then again you use one 5 by 5 by 6. Note that this is 6 activation maps. You have to convolute everything. So you will get maybe 10 such filters, and you will get 24 by 24. 2 will be deducted this side, 2 will be deducted this side. Okay. So then you will get another one. So 24 by 24, how many you will get? 10 activation maps. And then go ahead. And there is one concept called pooling, right? Pooling is, I didn't put here. Pooling, I'll just tell you that. What it does is, suppose you have got 24 by 24 by 10, right? Now you take each activation map. You take 124 by 24, then maybe you use 2 by 2 windows, right? And you take one representation of 2 by 2. Suppose you have got 2 by 2, so there will be 4 values here, right? One value may be 1, another one 2, another one is 0, another one is 4. So most popular use is the max pooling. What they take is that out of these 4, you take the maximum value and return it. So if you just do that, here 2 by 2, then 2 by 2 again, 2 by 2, so it will become half. So from 24 by 24, you will get 12 by 12. Okay, so you will get 10, 12 by 12. So you are reducing, right, the size, the dimension of the image. So max pooling is one. There is average pooling. Okay, so several other functions are used to do that. So average pooling is better in my opinion, but people and max pooling also works here. So this is the convolution layer, and finally you perform quite a few such convolution layer, a put convolution layer as well as pooling layer. So ultimately, maybe after a couple of years itself, you will get a 6 by 6, right? Here, feature maps, maybe you get 5 or 6 or something like that. So 6 by 6 by 6. So it will be very small, right? 36 into 6, and you can do that on one fully connected layer, right? What in MLP we have seen, and then we can classify the data. And learning, again, the same backpropagation learning, whatever we have seen, is used here. Okay, we have learned already that mathematics as well as how does it learn. We will need some eta and all those stuff, the momentum, and we can learn. Another surprising thing is that they are saying backpropagation may be little bit computationally high, right? Complex. That's why maybe sometimes what they say, you select randomly the weights, okay? You get the output, then you randomly select another set of weight, you say that. So instead of using backpropagation, nowadays just random selection of weights. So you keep on doing that, and it is expected that one set of weights will give you unexpected results. Okay, that is another good thing you can do, or you can use, say, some evolutionary technique, as I said earlier, can also be used or is also being used to train this convolution layer. Okay, so this is the use of convolution layer just to reduce the number of parameters in the network. We use this CNN because in the fully connected layer or in MLP, we try to extract or see the features maybe present everywhere, but that is not the case, right? In normal objects, maybe some features are present only, and we can small features we can just see that, and later it will be convoluted together and it will generate some meaningful features. Now those features, as I said, may not be perceivable by us, right? Our eyes or our feelings may not be able to perceive that, but doesn't matter. If machine can perceive it, that's fine, because machine will be able to, we try only to predict it, right? So that is what we do. Now there is another issue for this. Suppose you are working in video, right? You are looking at a video stream and trying to identify a particular incident. Then you have to look at the sequence of stream video snapshots, right? Matters. Suppose you are working to sentiment analysis, right? You are working on a text. So in that particular case, a text is nothing but a sequence of words. Now, same word maybe put in a different sequence will have a different meaning, isn't it? So sequence matters. Moreover, text may be of consist maybe 10 words, another text may consist 100 words. So different text may contain different amount of words, right? So variable length and all those things. Another popular example, people say that we try to predict what is the next website a particular viewer, right, who is browsing, so is going to expected to see, so that machine can keep it ready, or server can keep it ready, that okay, user may be looking for this particular website, so that they can fetch it earlier to make it faster, right? So there two things matter. One is size, may not be consistent, like all the images are 32 by 32. It is different size or different in numbers. Another thing is that it may be sequence may matters, right? So in those things, the CNN or MLP does not work well. Okay, so what they have given is the recurrent neural network. Okay, so in this particular case, this is the example and very simple. So there will be different steps, right? So you feed the first word maybe here, second word here, third word here, and it is a something recurring features or recurring ability, right? Recurring input ability you have to take. So if you have say 3 words, you can use this. If you have 5, 6, 7, 10, does not matter, right? So whatever the output after the first input, that would be fed together with the second input. Okay. Then after obtaining whatever you get the second output, that would be fed together with the third feature objects. Okay, like that. So this is the way it is being done. And note that here the weights, there are 3 sets of weight. One is U, one is V, another one is W. They are same. Okay, they are not different. So you are reducing the number of features or parameters here as well. So recurrent neural network is a very popular one, but there are some drawbacks of it. I'll just tell about this. This is a deep network. This is the one they call vanishing gradient problem. Suppose you have a text, say maybe 100 length. Now after say maybe 100 or maybe the 50th or maybe after 10th word, maybe the impact of the previous words, right? Maybe just immediately earlier word, the impact maybe it will be able to remember, but the impact of the earlier things may be very low. So that is a problem. There are different ways to handle it. You can look at it. There is another popular one which we are very much interested on, and in fact we are learning, you can say that is called generative adversarial network. Maybe Swarup has used it more extensively than me. Okay, I know that. So GAN is a very popular one. This is actually introduced or invented by Ian Goodfellow. He has a very famous book, Deep Learning. You can buy that book. It's worth buying it. So Ian Goodfellow is a very young guy. Okay, so you can buy this book and learn about deep learning. And he has invented generative adversarial network. You know that the primary objective or the requirement of this particular network was this. So far, whatever we are talking, right? So far, whatever we talked about, we have a training set. We want to learn the pattern and summarize the pattern, right? It is easy to infer, to come to a conclusion about a population. Say you study the data of a population, right? You collect a set of data and you come up with the gist, right? Summarize that. Summarization is easy. Now, how about generating a particular sample in that? So you study the pattern, like the example we have seen, right? Say Picasso used to paint. Now you study several paintings of Picasso and learn the pattern, and you generate one painting of Picasso. It is very, very difficult, even for a human being, right? You might have seen say, several faces, right? So far. Now, if you ask me to draw, I cannot draw. I cannot draw well. Okay. So it is very difficult, frankly speaking, to generate a sample. And again, that's why it is generative adversarial network. It's a very, very what shall I say, famous invention, I can say. Okay, so what they do is that you have got, say, real world, okay, real world data, and then you generate a model. They'll study this real world data and will generate some synthetic observation, synthetic sample. Okay, that is the objective of GAN, and for that you have got 2 parts here. One is generator, another one is GAN. One is generator, another one is the discriminator. Okay, so we have got the generative model, another one is the real world. Okay, now this generative model and actually this particular network, they analyze the real world data, they come up, they try to extract the different features of this real world, and they use this generative model uses those features to generate to come up a synthetic image. And this is one example. They have, you can see that, and this is actually, I'm not going into detail about this, frankly speaking, and maybe we'll arrange another one later. And if any of you are interested, you can contact me separately, and we can discuss about that. And this main thing is that there is one discriminator, as I said. Here, the generator tries to fool the discriminator, and discriminator tries not to be fooled, frankly speaking. Okay, that is the main concept, and game theoretic concept is used here to populate this one. There is detailed mathematics here you can look at, and frankly speaking, right now, since there is not much time, I am not, and another thing is that I'm also a bit exhausted. So maybe I'm not in a position to explain everything. Maybe later, right? If anyway, if any of you is interested about this, please contact me later. I'll be very happy, glad to share my understanding about this with you guys later. Okay. With this, I am stopping here, and I would leave it to Swarup so that he can complete this particular session. And I'll be again happy to answer your questions if you have any.
In fact, we can have one more such program on only because we have learned now the basics. Then we can go for the most higher level, advanced level models like
Mathematics, even in MLP and all those stuff. Yes.
only purely on that only. Hope we may able to do one more such course in the near future. Hope so. Fine. Thank you, Dinabandhu. Such a nice way you have presented the difficult concepts. Hope it may not be possible to understand in a single shot, but possibly it will going to give some sheet points to everyone's mind to start on, because most of the cases the ideas whatever it is there, something may not be very firm, but when someone can see the underlying engineering behind the different models, hopefully that may help them to understand it better ways any of the model. So that's why I feel it's very unique kind of. I told at the very beginning that you will most of the participants also appreciate that this is kind of a something unique kind of a workshop or faculty development program that we have conducted, where we are going in very inner details of the mathematical insight. That's why we have given the name mathematical insight of every model, because without understanding those mathematics, maybe I'm not talking about we need to be a great mathematics like Dinabandhu, but at least the intuitive idea, if you can draw, then also it will going to work. Because at the very beginning I said that most important is the tuning of those parameters, because we take always run those packages whatever it is there, you get default parameters, and because of which sometimes it's work greatly, sometimes it doesn't work. So that's why we need parameter tuning, and to do the parameter tuning you have to know what is the role of those parameters.
Exactly.
So that's why these kind of workshops is very useful to every the data science lovers or machine learning lovers, and hope we're going to have one more such a program in very near future. Let's see how I'm not going to make it more delay. Let's see after once we complete our examination sessions and all, I'm going to have one more such one. It will going to be a sequel. It will going to be part 2 with the deep learning models that we're going to learn from the Dinabandhu. So with this, I'd like to make it open to all the participants to get your feedbacks about the overall event. Of course, there is about speaker is it's I personally am always remain speechless. I always appreciate Dinabandhu looking into his skill, the mathematics. Normally, this is the work of the mathematician, but hardly the pure mathematics people, they come into that computational area and then they try to explain in that way, which is very rare that I have seen. Either they are purely the computer science people who having less knowledge about the mathematics, or the mathematics they try to work in their own domain instead of switching from that mathematics to the pure computations. So there is nothing to say about Dinabandhu. So whosoever is about to give take out your feedbacks, it's open to you all.
Yes, Vinan.
In
Yeah.
fact, in adding to Binong, I was thinking about like I would like to give a proposal to Dinabandhu Da. Dinabandhu Da, please start writing a good book on the same title. I should prefer give Basics of Machine Learning, the Mathematical Insight. I have proposed that name. I think you may able to utilize in the future to write a book with the same title.
Yeah, you know that there are several books, but yes, actually, and different books are focusing on different aspects of machine learning. I'll just tell you a couple of books which are helpful, at least for me. One is that Introduction to Machine Learning from Data of Yasser Abu Mostafa. That is a fantastic book to learn the basic theory of machine learning. The second book I'll ask you to read or refer whenever is required, that is Artificial Neural Network and Learning Machines of Simon Hekin. Okay, these two books you can keep with you, and for deep learning, I'll ask you to refer Ian Goodfellow. These three books I have seen fantastic, and if you can go through them, yes, I guess you will be able to learn. But consolidating everything, it is really very difficult job. Maybe people like Swarup will be able to do that. Let's see. When we meet, we'll discuss about that. If we can come up with a concise materials, we can generate some concise material about this machine learning. Thank you, Swarup, for the proposal.
In fact, I can help you.
Yeah.
I can help you getting a good publisher, world-renowned publisher.
Okay. Very good. Let's see.
And let's
I'm
see.
a bit lazy in that, you know. You know.
So, like, thank you for this wonderful workshop. So, most of the FTP which I have attended is normally tool oriented or application oriented, and this is the first of kind where you have shared your conceptual understanding. And I was, particularly able to understand the SVM model which you taught SPN today, and I'm very much thankful to you. And yeah, like hope this workshop continues in future also. Thank you, sir.
Okay. Welcome.
For myself, thank you, sir, for giving us depth, knowledge on the mathematical part of SVM and others. And normally the dependence on the library, basically we are now deviating from the main mathematics nowadays.
Yes.
So now this workshop really helped me in that. And I also like to request Roy sir for organizing another one, as you said, on deep learning, basically. All theory on deep learning like GAN and reinforcement learning. So it will help us a lot, sir. I'm
Yes.
very interested in that.
Okay.
Hello, sir.
Sumit.
This is Sumit. Thank you, sir. First of all, thank you very much, sir, for all your learnings I have got from you. This was a great learning week. Though I might not get all the concepts, but I'm sure that in near future, when I will study the concepts. I will go through these lectures of yours, and I can relate it. Uh, as Swarup sir was very much optimistic about you, he was telling you was a great gem in mathematics. So I can now relate that. And thank you, Swarup sir, for conducting this workshop. This helped me a lot. Thank you very much, sir. Hope to meet you soon physically after the pandemic overs.
Yes. That would have been very nice, actually. We would have been stayed together, discuss, right?
Yes,
And
sir.
not
Yes,
only
sir.
the classes, but outside also. Then in more interactive, it would have been much better.
Yes, sir. Yes, sir. Hope to meet
Yes.
you soon, sir.
Yeah, sure. Okay, Swarup.
So anybody would like to add, or we can now.
I have one thing to say.
Okay.
You see, I like talking. I like sharing my understanding with others, and I will be very happy if you can use whatever I conveyed to you guys, little bit of it, and apply and use it, I'll be very, very glad. So that is my expectation. And moreover, in future, if you have any issue and if you feel that maybe if you contact me, I'll be able to somehow help you out, or something, show some uh, way to come out of those issues. So I'll be much more happy. Okay. With that, I just want to say.
Definitely. I also hopeful that that was my actually initial idea. Like it should not be like just to have some kind of workshop, which is like kind of a superficial. That I really don't like. For last several years, we have passed through such kind of courses, but I have never. I mean, I always had a feel like we should have a very detailed discussions on some of the small topic, and that is the reason why thought of to go for a such kind of small but more effective workshop. If we
Yeah.
can, definitely it will come to more form into that.
Even with say neural network itself, only say NLP, up to MLP, we can have 5 days workshop.
Have this workshop, right? Different
So
models.
that is same also.
Right, definitely.
Good afternoon, sir.
Yeah.
I cannot say that I have understood everything because I am totally new to this area. But then the mathematical derivation, the explanation, whatever you have given in the simplest language, it was really interesting. I have tried to understand, and then for my future reference, I have tried to record few lectures also, because since in laptop the screen recording is not possible, but still somehow I have tried, so that later, like when I start working, so that if I have any doubts regarding any of the areas, so I can refer to your lectures, I can go back to the video and then look into that. So it was really nice interesting lectures we had this 5 days. Yeah, I know it's not whatever you have given, it's just a basic things, but
Yeah.
when we start actually working, then we have to go in detailing, like when we have to work into the algorithm, the mathematical parts is there, but then when we're doing the programming, it becomes a little bit different. Like you don't know, if you get stuck somewhere, then it'll be very difficult where the problem arises. So in future, when we start working, hopefully whatever we have learned in this 5 days will be of some help. And thank you so much. And as you said, like we can always contact you, so if anything encounters your we'll get the email IDs from Saurabh sir, so we'll try
They are
to
actually my
keep in
presentation.
touch. Yes, sir. And you have given us all your presentations, your PPTs or notes, which is generally it's not very common. Like we have attended so many lectures, people are not very like keen to share their PPTs or whatever data they have. So thank you so much for all the data you have shared with us. And thank you, Saurabh sir, for organizing this FDP. It's really helpful. And regarding exams, I hope we'll be we'll get through the exam which will be conducted on Wednesday. Okay, thank you so much, sir. Thank you, Saurabh sir.
Thank you so much.
Yeah, so thanks a lot to Professor Bhandari, Professor Roy, and Mr. Datta. And since I'm not from at all either computer science engineering or pure mathematics background, and the mix of kind of managerial and technical role. So as Professor Roy had rightly mentioned that the mathematical concepts underlining these things. So really appreciate the way you have, sir, delivered these lectures. So many thanks, sir. One request: if the best, as with your experience, you have mentioned the reference books which we should refer. That list, if we get, then it would be really nice.
You
Thank you.
can download them actually from, it is available in the web, in the net. Those books are available in the net also, except maybe deep learning.
Okay, so those names, if Mr. Datta can send us in the WhatsApp group, so
In fact, I
Yeah,
have
it's
referred them in some of the presentations as well. You will find them. Okay.
okay,
And if you have any difficulties, you write to me, I'll send you back.
okay, thank you, sir. Thanks.
So then let us wind up
Yes.
today. So I would like to thank all the participants for your motivations, for your inspiration behind to attend a workshop like that. So
Yes.
we will continue. We normally called it as a Techno Talk series. So this is actually the second Techno Talk series. Hopefully we can have 3 or 4. And one of the series, Dinabandhu may again appear, and to have one 1 week's workshop. Maybe physical, maybe offline. Okay.
Yes.
So with that, best of luck to, best wishes to all of you. Thank you so much. Thank you, everyone.
Thank you.
Thank you.
Bye bye. All the best.